Nuclear power is a very, very expensive way of boiling water. Instead of a nuclear fission, a nuclear chain reaction causing a nuclear explosion, nuclear power plants control the chain reaction. They channel the massive energy of what would be a mushroom cloud instead into heat, a massive amount of heat. And we use that heat to boil water. That's what a nuclear power plant does. They boil water. The water makes steam, the steam spins turbines, and the spinning turbines make electricity. It is a logical process, but it has two problems. First, even when used as directed, making power this way produces nuclear waste, radioactive, dangerous waste that can, in some cases, can even be turned into the raw material for nuclear weapons. But second, beyond the nuclear waste problem, nuclear power production is kind of a high-wire act. When the whole idea behind what you're doing depends on this plant controlling a nuclear chain reaction, you really can't afford anything that might interrupt your control. In most reactors, if there's any sort of local disturbance, say an earthquake, the nuclear chain reaction process is immediately shut down. Control rods drop into the hot nuclear core to stop the fission process. But even when it's not still, in effect, turned on, that nuclear core is still so hot that a lot of things still have to go right in order to keep something really bad from happening. Have you ever noticed that a lot of nuclear power plants are right on the shore? They're right on top of a water source? If you tend to think of nuclear power plants in terms of the possibility of radioactive leaks or emissions, it can be unnerving to see those nuclear towers there right on your local river or your local coastline. But the reason they're right on the water is because they use a huge amount of water to cool down that unimaginably hot nuclear core. Even when the process of nuclear fission is stopped, the nuclear core is so hot, it needs a constant and heavy supply of cool water to be cycled around that nuclear core in order to dissipate its heat. Pumping huge amounts of water through the cooling system to dissipate that nuclear heat, well, ironically enough, that actually takes power. It takes electric power, even if the plant is turned off. So if an earthquake or some other disaster is severe enough to cut off electrical power to a nuclear power plant, if it is severe enough to disrupt the backup systems too, if the power is off and water isn't flowing through those tanks to dissipate that heat from that nuclear core, and that core will, over time, turn all the water in the cooling system into steam. It will start to evaporate. And if the power is off so long that the water evaporates so much, that the water levels fall so low, that the nuclear core itself gets exposed to the air, its undissipated heat will cause what is called a nuclear meltdown. I'm not using that as a metaphor, I mean it literally. A meltdown of the nuclear core. It overheats, it melts through and ultimately destroys the reactor. And then we pray that whatever containment facilities built around the reactor are sufficient to actually contain the disaster. Today at 2:46 p.m. local time in Japan, the Tokyo Electric Power Company reported that 3 reactors at a nuclear plant called Daiichi were shut down due to the massive earthquake in that country. Here's the important thing to note. At 2:46, at that first announcement, they said they had lost electrical power that they get from off-site. But they said they'd been able to switch to their backup, to on-site diesel generators. Remember, the earthquake that hit Japan was offshore. The tsunami caused by the earthquake didn't hit shore until about an hour after the big quake. So at 2:46, after the quake, but before the tsunami, the reactor is shut down, right? And they lost power. But their on-site generators were working to keep the thing cool. But then 55 minutes later, at 3:41 local time, a second announcement came from that plant. Now, the backup generators were out too. We don't know if they were knocked out by the tsunami. The timing seems right. But the backup power source failed. So then the Daiichi plant was down to just the fail-safe for the fail-safe, which is battery-powered generators. And those only last as long as the batteries hold out if they can't be recharged. The stakes here are high. If they cannot keep power on to keep water circulating through the cooling system around the nuclear core will evaporate the water that is surrounding it. The core will ultimately be exposed and it will melt down. And that is very bad. Authorities initially evacuated a 2-mile radius around the Daiichi plant. They then extended the evacuation area to 6 miles. As they vented the steam being produced by the water that is in the cooling system, the Japanese Nuclear Safety Agency said radiation levels had risen to 1,000 times normal in the control room of that plant. Officials reportedly described radiation levels 8 times normal at the gates of the facility. Japan has declared an atomic power emergency. The International Atomic Energy Agency, and this is the good news part you've been waiting for, the International Atomic Energy Agency says mobile electricity supplies have arrived at the reactor site. Japan has more than 50 nuclear power plants. At least 10 reactors are offline because of the quake. In addition to the Daiichi plant, they also this evening declared another emergency at a plant called Daini as well. This is where the Daiichi plant is, and this is where the Daini plant is. You see they're nearby. We've also marked Tokyo on this map so you can see where that is, as well as the epicenter of the earthquake so you can see how this all fits together. Joining us now is Edwin Lyman. He's senior scientist at the Union of Concerned Scientists. He's an expert on nuclear power. Dr. Lyman, thanks very much for your time today.
It's great to be here.
Between the two of us, there's only one PhD in physics, and it is yours. If you could start by letting us know if anything that I just explained, if I misstated anything, or if there's anything critical that I left out.
Actually, it was technically flawless, and I think you should get an honorary doctorate in nuclear engineering.
Well, this is starting off very, very well. I like the sound of this. Is there anything about how the situation has progressed over the last few hours that makes you feel any better or more reassured about the chances of preventing a big disaster here?
Unfortunately, I'm getting less reassured with every update. The news that the incident was affecting not just 3 reactors at Daiichi, but also a number of reactors at Daini, indicated that the authorities were not being upfront a long time ago in their dealings with the public, and just makes the situation seem as if it's escalating out of control. So I'm really worried about what else we're not being told at this point.
When the authorities have put out statements today about pressure in some of these reactors rising, we saw one report today, for example, that pressure in one of the Daiichi reactors was more than twice its designed capacity. What does that mean? What are they talking about with pressure? How dangerous is that? How do you alleviate that pressure?
Well, the danger is that, of course, as the reactor gets hotter and the containment atmosphere gets hotter, the pressure will increase. And in order to avoid a potentially catastrophic rupture, the hope is that you release some of the pressure by venting some radioactive gas now and avoid a larger catastrophe later. So it's really a devil's bargain, but of course the radiation exposure resulting from moderate venting is going to be a lot less than if this accident actually progresses to a worst case, where we have a full-scale core melt and then a catastrophic rupture of the containment.
To be clear about that venting, that essentially is a controlled, deliberate release of some amount of radiation. And obviously that's a better scenario than an uncontrolled release of a lot of radiation. But is there reason to be concerned even about what has been vented, even though it's been done on purpose?
Well, any amount of radiation is a hazard. It's an established fact that there's no safe level of radiation. So, of course, any artificial radiation introduced into the environment is a concern. But I think, I understand the logic behind doing controlled venting at this point, and I think we all just need to hope that it's going to work, because if there's a catastrophic rupture of the containment and a large-scale core melt, we could be facing something like Chernobyl as opposed to something like 3 Mile Island. At 3 Mile Island, as bad as it was, they were able to avert a full-scale containment failure, and there was a release of radiation, but it was comparatively small. But of course, you're dealing with comparatives here. You have 2 unpalatable choices, and you have to decide.
I don't mean to ask you to explain the obvious, but just looking at these images from Japan today, confronting the certainty of hundreds of deaths, the likelihood of more than 1,000, if not thousands, of deaths, confronting the certainty of billions and billions of dollars worth of damage. If there is a If there is a nuclear meltdown, and as you say, we could be looking at something as serious as Chernobyl, does that make this a global disaster in addition to being a Japanese disaster?
Yes, I think in a number of ways it does. First of all, Chernobyl did inject a lot of radioactivity into the atmosphere, and that did go around the northern hemisphere. There were certain aspects of that release that we probably wouldn't see here. It was a much hotter plume and it went much higher. But I think we can expect there will be some detectable radioactivity if there were an event of that size in Japan. But also the other ramifications are clearly economic, and also they have to do with our ability to mitigate climate change. Our organization, UCS, is not opposed to nuclear power per se. We do worry about climate change, and we understand nuclear power is one option. But we shouldn't take that option off the table by running nuclear power plants in an unsafe way, because obviously a catastrophe like this could really eliminate the possibility of that option. So we believe that nuclear plants really have to make an extra effort to be as safe and secure as possible. And unfortunately, that doesn't seem to be the attitude of the nuclear industry, either in the United States or abroad.
Let me ask you one last question about that attitude and that seriousness about safety. If there is a meltdown, God forbid, at either one of these affected nuclear power plants that have now been declared emergency sites by the Japanese government, we will be counting on the containment units around the reactors themselves to confine the damage. Just so we understand it, can you just explain for a lay audience what a containment unit is like, if one's ever been tested in a real-life disaster before, and if we should assume that they might be compromised by the earthquake and the tsunami themselves?
Well, the containment structures are generally reinforced concrete buildings that have a leak-tight liner. And the idea behind the containment is really, if you have what's called a design basis accident, where you have a partial melting of the core, but you don't have any catastrophic explosion, that containment will function to limit radiation releases. Unfortunately, after most reactors operating today were designed and built, they discovered that, well, there are certain types of events that could challenge the containment, and they're not impossible. So most of the containment buildings at reactors today are vulnerable to certain severe events that could threaten their capacity to contain radiation. And unfortunately, the Mark I boiling water reactor, which is what we have at Fukushima, has vulnerabilities that people have known about for a long time, that if there were a core melt that escaped from the reactor vessel, it might also breach the containment. And so I think there's a wide range of containment buildings out there, but I am concerned about the Mark I's in particular and their ability to contain radiation in this event.
Dr. Edwin Lyman, senior scientist at the Union of Concerned Scientists, you have helped me understand this better, and you have not set my mind at ease at all. But thank you for helping us explain it. Thanks a lot.